everyone. This is Ruchi Divakar from A3R3 Quandary. Welcome to In and Beyond with A3R3 Quandary. This is our first podcast for all the science enthusiasts around. On this podcast series, we will be talking about topics you may have come across and we will have a discussion on them. On today's session, we have Madhusudan Srinivas and Amir Hussain, who are our in house geeks. You can say. We will organize these podcasts every fortnight and we will bring you topics that may find your interest. Let me begin the show by telling you guys that, we've been thinking of having this session from a very long time. We've been discussing to have this podcast from almost more than a year, I say. But somehow things didn't work out and we were not able to, uh, you know, record these sessions. But today, fortunately or unfortunately, in the situation where Corona is out and we are in and we are having this session. Thanks to technology, I would say. So let's begin the show once again by addressing the elephant in the room, coronavirus. All right, Madhu, what do you think? What do you think? What do you think about the situation we are at, and how would you describe today's scenario?
Hi, hello all. Good evening, good day. So yeah, it's a very interesting times that we are in. Uh, Challenging definitely, and if we can find some stuff worthwhile to keep ourselves occupied, yeah, it's a very interesting time.
True. So, Amir, what do you have? I mean, what is your take on Corona now? I mean, the situation we are at.
It just feels like we are in a movie right now, in a like post-apocalyptic movie
Yeah,
that we've all been watching and all love. And it for a short time, at least in India, it looked like that actually. The roads were so empty, basically. So it was a good sight to watch, and also like it was freaky, if you ask me.
Exactly. I would agree with that point. And I would
Yeah.
say, this is something in this situation. This is like something I never thought, I would ever see or I ever hear or go through this situation in my lifetime. And I'm sure everyone would be thinking the same way.
Yeah.
I mean, yeah, this is crazy. All right. So we are here to talk about in and beyond. So what is in and beyond for you guys? I mean, what is in and beyond, let's say, Earth? So Madhu, let's start with you.
thank you. So the focus of this podcast, my view of it is a lot of us have always been as kids we are all really small, tiny little explorers, experimentalists, right? We keep trying stuff. We just want to know how things work. And many of the times we learn the hard way of what things to do and what not to, right? So
Right.
somewhere in the process of growing up, that intuitiveness or that inquisitiveness is lost, is what I personally honestly feel. And it's unfortunate that a lot of people are. I hope that there are a lot of people who are interested in the sciences and who are mind blown, captivated by what happens there. So
True.
the aim for me from my end for this podcast is for all those people who have always been interested and have not got the avenue to explore it. We present them with a picture as simplistic as possible of what's going on there, out there, both on the planet and beyond our planet, in the realm of science. And we hope we can interest many more people to this topic. So yeah.
True.
Yeah.
Well,
That's
thank you, Madhu. Thanks a
beautiful.
lot. And Amir, what is your take on this? I mean, what would you
So
say? What is it and beyond?
I would just say a simple thing. Uh, I had this thought like a few days back. Space is the only place where life, I mean, the birth, life, and death, all three are magnificent. basically. When something is born, it's magnificent in space. When something is like in its life period, basically, like for example, our sun, basically, it looks so marvelous, so fascinating. And then the most craziest part is like even the death of something in the universe is beautiful actually. Look at black holes, like how they are formed basically. So
Right.
that says something like uh, we just need to ask the right questions, if you ask me. So like let's continue this journey. Basically, we'll have fun talking about these topics and beyond the universe and within the universe, every single thing, because universe is basically us, right?
Right.
So right now we don't have evidence of any other people in the universe apart from us, basically. So it's just science of us, basically. So how we perceive the universe. So it's always good to talk about these things, and it's always fascinating to talk about these things. And
True.
it's going to be good.
Wonderful. All right. So I hope you all will enjoy this session with us. Welcome to In and Beyond. Let's begin the show. What's say, guys?
Yeah.
Yes, sir. Let us do.
Wonderful. So, the first and foremost doubt and the biggest question what I have in my mind, I read it somewhere. What I want to know is why our sun can't become a black hole at the end of its life. Wait, before anything else, what is a black hole? Let's start with that. What is a black hole?
I'll try to put across my understanding. And so, even before we get to the topic of the black hole, we need to understand, we need to know that there are uh, forces at play, right? We see light, we feel light, the current, the magnetism, the gravity. So, all these are variations of forces. Now, there are four fundamental forces. One's the strong nuclear force, which is keeping the protons within the atom, the nucleus of an atom together, even though they are like charged. Like as one would know, protons are positively charged, and whenever you have most of the charge together, they don't want to bind together. So if it's a positive and a negative charge, they stay in one place, either cancel out each other, or if there is some form of barrier or condition to keep them together, they will stay that way. But you won't find the same thing when things are like similarly charged, like two negatively charged particles won't remain together, and same with positive particles. Now protons is at the nucleus of an atom. The nucleus of an atom is made up of what? Two basic stuff. One's the neutrons and the protons. Protons are positively charged and neutrons have no charge. Now the strong nuclear force is that force which keeps the nucleus together, the protons and the nucleus together. That is the strongest force that we know of and that we have detected. And next moving is the second fundamental force, which is the weak nuclear force. Now, the weak nuclear force is the force at play that's keeping the electrons still in part of the atoms. So, atoms, as small they are, as tiny as they are mostly empty. Like to give a perspective, if you had to blow up an atom to real life sizes, you blow up the nucleus to the size of probably a mustard seed, right?
Hmm.
And the mustard seed will be right there, right in the center of a football field. Now we all know how huge a football field is, right? Now a mustard seed at the very middle of a football field is what the nucleus is, and there at the very end, the stands is where the electrons would be revolving. So there's a huge gap between the nucleus and the orbits of the electrons, and yet the electrons are still held together as part of an atom. So that force, which is keeping the electrons as the part of an atom around the nucleus, is the weak nuclear force. Now, this is the second most strongest force. The third fundamental force is the electromagnetism, the force of electromagnetism, and the easiest or most relatable effect of it is light. Right? What we see is a very narrow spectrum or a very narrow band of what the light spectrum really is. You have infrared, you have uh, X-rays, you have gamma rays, you have a whole spectrum of light. And what we are able to see, you and me, is just a very tiny bit of that light spectrum. And light, that's the third, sorry, the electromagnetism force is the third most strongest force, right? It is third in order, and yet the range of its effect is immense. When I say immense, imagine this: when I'm at one end of the universe and I have an atom, magically speaking, I have an atom in my hands, and I'm able to somehow strip the protons from the nucleus apart by a few feet across, and they would have not much influence on each other at all. So their field of influence is small. It's huge when they are together. For example, uh, if if there was no neutrons and no other uh, gluons, the particles that are keeping everything in the nucleus together, if none of them were there, and if I had to just put two protons together, they would immediately go away from each other at speeds of around 8,000 kilometers an hour. Sorry, 8,000 miles an hour. So that roughly translates to about 15,000 kilometers an hour. That's the speed at which protons just move away. But they have to be really close for them to have effect on each other. Now, at this end of the universe, I am picking up the protons, move them away by a few feet. They almost do not have any influence on each other. And if the farther I move them away, not much. So let's move across to the once again back to the electromagnetic force. Now, again, I am at one end of the universe, one corner.
Okay.
Not that it has corners, but let's just imagine that. So from one corner, I shine a light, right? I flash a torch light. And
Okay.
Ruchik, let's say you are on the at the other side of the universe,
All right.
and
Okay.
yet you will be able to see this light. This light will reach you. Of course, it will take a lot of time. You'll only have to wait for 98 billion years.
Wait, what?
98 billion years.
98 billion years.
98 billion years. So
So
that
you mean
that's
to
that's
say
the that's
that
the expanse or the size of the universe as we know, the observable universe.
okay, okay. So you mean to say that you will be flashing a light from one end. If someone is flashing a light from one end, and I'm on the other end, the observable universe, both ends of the observable universe. Now, you may say that the light will still travel for the entire 98 billion light years.
Yep, that's the beauty of science, physics, electromagnetism, I suppose.
So that means to say, like, someone may have flashed a flashlight several years ago, and it may be coming on to me sometime soon.
Yeah,
Precisely,
yeah.
That can happen,
precisely.
right? That can happen.
So, just to elaborate on that point, the sun that we see is not instantaneous. We are not seeing as it actually is at that very precise point. So, we are seeing sun at our end, and if we had to move to the sun, what you are seeing has already happened here, but it takes light 8 minutes to reach us. So, the sun that we see is 8 minutes older. There is a lag. There's a cosmic lag of 8 minutes between us and the sun.
And
So,
that and what you're saying is wait. Let's rephrase.
You're looking at the sun's past,
So
basically.
basically, we are actually looking at a
yeah,
negative side. So, matlab,
Let's
so
You
the
could
thing
say
is,
that. Yep.
what we are
let's
getting
time travel to you.
is the stale light, right? It's an
Yep.
8 minute stale light. So that is applicable to all the other planets as well. I mean, all the other light giving objects as well, right?
Even there is
Of
always a
course.
delay, Ruchit. See, even when I'm looking at you right now, not even on the computer right now, okay, even if you are standing in front of me, no, there is always a small delay. There I am seeing, looking at you in the past, basically, because the light takes time to reach me, basically. Your light takes time to reach me. It is very small. It's not even like it's
Yeah,
negligible, basically.
yeah,
But
negligible.
still, nothing you see right now or nothing you see ever is as it is,
Now you're breaking my bubbles, guys. You are breaking
basically.
my bubble. So in the night sky, when I see a star, I'll be like, oh, how beautiful. So that may not be there, is what you're saying.
No, I mean, it may not be
They
there,
may have
basically.
exploded, died a few
Long time.
hundreds, if not thousands, years ago. But yeah, you got the gist. You got the idea. Yep.
Why? Why? Yeah,
Yeah.
as you said,
So you may have been wishing on a dead star
oh,
Yeah. Fishing on a dead star.
okay,
All the
wait.
best.
and your
That's the
grandma and
case.
grandpa are not there.
Wait, if that's the case, if someone is looking at us, maybe someone is looking at us. So they may not be getting the same light what we are, right? I mean, they may not be getting the real image what we have it right now. Am I right? I mean, am I nearby somewhere?
They will see us as we were before. Maybe even if someone is very far away, maybe they will be seeing like dinosaurs on Earth, basically. If they have high power telescopes, basically. Correct, Madhu? Right?
Yep. Exactly. So the
Wait,
dinosaurs lived 65 million years ago. That is when they went extinct. Now, if you have an advanced civilization which are, say, around about the same distance from us, 65 million light years away. And if they had an enough powerful telescope, that telescope will have to be the size of our solar system. And that is, I don't even think that is even close to what it must be actually. They'll need to have such a big telescope to just peer through space and time. And if they pointed it towards Earth, yeah, they might find even dinosaurs roaming around. Not saying that it is possible, but a thought experiment. Yeah, of course.
so basically, like if we are right now, I mean, our scientists are looking into the night sky and into the space from several years. So they've been observing, and not just our solar system, outside our solar system, they are actually finding out different solar systems and different, what is it, they are trying to find out magnitudes and magnitudes of, all the other things. I mean, in the sky, the space. Do you feel that whatever we may be seeing, they may not be, they may not be seeing the right light, right? So let's say, for example, there is an Earth somewhere where there is civilization like us. They are same like us,
Advanced civilization.
advanced civilization, or let's say even like same like us. Let's say someone's there out there somewhere. Now, right now, when we are looking at them, maybe because we may not be getting the real, I mean, the latest light. So we might be getting a stale light on their planet. So we may not even see them, right? Same like they can't see them. We are kind of invisible one.
Exactly. So, uh, like we're talking about this before, it takes light 8 minutes to reach from the sun to us, right?
Right.
So, and the power of electromagnetism, even though the force is not that strong as the other two forces, the strong nuclear force, the weak nuclear force, the range of this electromagnetic force is huge. The observable universe and beyond, if we do observe something beyond it someday. So that is about the electromagnetic force.
All right. It's too much information, man. I desperately need a break. All right. Just give me, let's take a break for some time and let's be you right. What's it? Good.
Sure. Yep.
All right, guys, see you back. And once we come back, we'll start again with relativity. All right, ladies and gentlemen, welcome back to In and Beyond with A3R3 Studios. I have Madhu and Amir with me. We are talking about so many things. We are back to the topic of black holes. So, Madhu, you were saying.
Yeah. So the idea of black holes came from the mathematical equations that were part of Albert Einstein's general theory of relativity. This he proposed in the year 1915, right? So this is how he imagined. So the medium, what we can see or observe between, let's say, now we are standing here and look up at the moon. What do you see? Just a black night sky and the moon. Nothing between the Earth and the moon. And the same even when you look down through the satellites. There's nothing really that you can see or observe. But however, Einstein said that the entire medium of the universe is this thing made up of space and time. So three dimensions of space, this, and I don't know if you can see this. So one going up, height, uh, length, and
Mhm.
the depth. Right. This is the
Okay.
3D vision that we all know of. So three
Okay.
dimensions of space and one dimension of time. That is how he imagined, helped us reimagine the universe, our understanding of the universe. So
Okay.
space and time acts like this. Uh, is the medium where everything is present. The Earth, the Sun, the planets, the other stars, the galaxies, black holes, the nebulae, everything, right? So, in order to get an hold of that idea, uh, here is how we would imagine it. Imagine a tarpaulin sheet, a
Okay.
sheet of tarpaulin, or say an spandex. No, the material used in all those superhero movies, all wearing spandex wears. So it's
All right.
very stretchy, very rubbery. Now imagine a surface made out of spandex. It's very elastic. It has a high rate of elasticity. Now you drop in a marble. You roll across a marble. What does it do?
Mhm.
It just rolls from one point to the other side, the other point. Now, let's say you drop in a stone right in the middle of that place,
Mhm.
and the next time you roll a marble, what happens? Instead of uh, reaching the other point or the other end, it goes into this curve or the depression that the stone makes in that fabric, and the marble just goes around it. And if it's not fast enough, it will still continue keep going around it until it goes to the center, right? So now replace this stone with a dense object like a star, for example, and the sun, our planet, is that marble. So we are just rolling along the depression that's been made by the sun in the
Mhm.
fabric of space-time. So
Okay.
it's not just sun attracting Earth like how we imagined it was, right?
Mhm.
This is how gravity works. Gravity is the variation in space-time caused by a dense object, and its effects are felt by the lesser dense objects like our planet. So this is what came out, or this is what he said. And then an year later in 1916, so if anyone remembers history lessons well, 1916 was when World War One was going on, the first World War.
Right.
Now, during this World War, German physicist, back then everyone had to be part of the war, and there was this German guy named Karl Schwarzschild. Now he was in the trenches, just working the trajectory of the bullets and the shells that were moving across the field, the battlefield. and he had just heard about this theory of general relativity by Albert Einstein and its implications, how it was uh, refreshing, a new look at the way the universe works. And he got latched on to a few specific ideas. One of them being that if there was a dense object and it was causing a curvature in space time, a dent in space time, and something goes in, and if it does not have enough momentum, it will just fall into that object, and if it has enough momentum, it just dips across that curvature and keeps rolling on, but it will still have it will feel the effect of this dense object. Now imagine, remove the star, let's imagine something even more denser than a star, which can warp space-time so much that it just how do you put it just uh, wraps around itself and falls within itself. Now imagine the sun just making a dent in the curvature of space-time. Now this example again. So this is space-time. Sun causes curvature, and you remove the sun, it's fine again. Now, if there is an even denser object than the sun, the curvature is so much that it just goes 360 degrees and closes on in itself. This keeps repeating to such a point where all the mass in and around that point gets concentrated into a very, very tiny point in space, which is referred to as a singularity. So this is what he said. This is how the uh, concept of this dense body, a black body from which nothing could escape, basically nothing, not even light,
Oh, okay.
right? So back then there was still no concept of the black hole, nor this term was coined. So, and later, somewhere in the 1960s or 50s, there was another American physicist by the name John Wheeler. Uh, John Wheeler was the guy who came up with the term black hole. So until then, there were discussions going on. This sounded very intriguing. Now, just imagine a point in space where nothing can go. Right? You lock a door, a person is blocked, but you will still be able to just come out of it somehow. Break open the door, or just use your head, pull out the latches, still be able to get out. Now, a point in space-time from where once light enters, even light cannot get out. Light is the fastest thing that we know, and it's touted to be the fastest thing that can ever be in the universe.
Right.
It goes at around 3 million kilometers per second speed, or 3 lakh kilometers per second. That's the speed at which a single photon particle travels. Now, at that speed, you put a concrete wall. Does it matter to that particle? No, it will just go through it. But then, it comes across the space of a black hole, and no, the black hole just says, "No, sir, you just cannot get out."
You may not
It,
pass.
yeah, you may precisely, you may not pass. So, this is how the idea of the black hole came. So a point in space, extremely dense, all the matter condensed into a point known as the singularity, and then the singularity has a gravitational effect around it, and that field where its effect is strong enough is called the event horizon. So whatever you see of the black hole simulations or the pictures, even the black hole picture that came out last year, you see
Right.
this just one black halo surrounded by a disk of light. So breaking it down at the very point, at the very center of that black thing, it's a sphere, right? That is
Mhm.
what we think it is. What the observations are. It is a sphere. Probably we may get to know that it's not sphere, it's not uniform, or it may just turn out that it's always a sphere. But this is the thing: you have a sphere at the center of which is the singularity, which you cannot see because anything that enters the event horizon never comes back. So you have no idea of what happens inside there. and then just around it you have this ring of fire. It's too enigmatic to watch, and when it's captured, when that photograph came out. So this ring is called the, yeah, what was that called? Amir Hussein, please help me out here.
I actually don't
Accretion
know.
disk. Yeah, sorry, accretion
It's
disk.
yeah, yeah, accretion.
Yeah. So it has
Sorry,
this
what was it?
accretion disk. Accretion. Accretion. It accretes all the matter in that disk around the black hole. So it's not as simple as saying something drops into a black hole and it just goes into the event horizon. No, what happens is something tries to get close to the event horizon.
It gets
Event
ripped
horizon,
into
the
pieces,
black hole.
basically. It gets ripped into pieces, basically,
Yeah,
before going into the black hole. And the
So basically, not everything
accretion,
can enter the black hole. Is that what you're saying?
no, nothing can leave the black hole. Nothing can escape it, actually.
Okay.
So, uh, imagine light is the fastest traveling thing,
Medium.
basically, of everything. Okay, there is even if a particle has even a little bit of mass, it will be falling behind the speed of light. Now speed of light is the fastest known, like,
Medium.
part
particle, basically. Okay, so now imagine,
photon is
like,
the part.
nothing can go past the black hole. Like, if anytime there is a point, not a point, there is a ring around the black hole called event horizon. So basically, this is the point of no return, basically. This is what Madhu was explaining.
Correct.
But this is all the, like, imagine a star coming close proximity to a black hole. Okay, so that star will not just sucked in just like that. Okay, as soon as it hits the event horizon, then what happens is this, the mass from the star, basically, like when the black hole starts eating the star, since the black hole has a circular motion, that speed is so huge that all this matter from the star gets stuck on that accretion disk, basically.
Sorry.
Get checked, dude.
Get checked.
Ah,
Yes.
accretion disk.
So if I'm not wrong, am I wrong, Madhu,
No, no, you're right. You're right. Please continue.
about this understanding? So basically, like, there's no escape from the black hole, basically. Okay, and then the only thing that actually, there is something that goes even faster than light. Can you, can Madhu, can you tell me what is it?
Faster than light.
Faster than
Yeah,
light.
Photon.
and not exactly faster than light.
Photon.
Space itself travels faster than light. Correct, right? Just imagine this. Okay,
One
space,
second. For now,
everything.
Amir, you're confusing me. Amir, you're confusing me. Now, Madhu just told that, there is nothing else which is faster than light, and now you're saying that space is faster than light.
But space is not a particle. Space is something that we are all on, right? So, right from the Big Bang, the universe is expanding. Correct?
Right, right, right.
You know about the Big Bang, right?
Yeah, yeah.
So, like, what is Big Bang, basically? The explosion of space, basically, right? So,
Mm.
light, matter, every single thing, whatever we see in the universe, is a part of space. Correct.
Right.
Of course, the space will have no limit, basically. It can travel like even 100 times faster than light, if I'm not wrong.
Right.
So this is
Even
what
more.
I've been hearing. So that is the only thing, not even a particle. It's not a particle. Space is not a particle. It's the only thing that can travel even faster than light, because it's space.
Mm.
So I'd like to add. So you have this medium, right? Now, this medium of space time, I'm not sure if it's clear, very descriptive, right? So this medium of space time, and then you shoot a beam of light, and it travels along space time, the medium of space time, right? Now, what if this space is stretching while this light is traveling through it?
Oh.
So this is what's happening. So just to pick on your mind a little more, you know how old the universe is? It's roughly around 14 billion
14
years old. Okay,
Okay.
14 billion years old. So when you say 14 billion years old, that should ideally be the size from or the length of the universe from one end to the other. It should be 14 billion years because the universe came into existence 14 billion years ago. So the universe can't cannot be bigger than this 14 billion years, right?
Yeah.
However, like I told earlier, what we observe
90.
is 98 billion light years across. So what is this? Why is this happening? This is not
So
an error in any calculations or any error in any theory. This is the observed thing. This is a fact. The universe is 98 billion light years across, even though it came into existence only 14 billion years ago.
so is
And
it
this
the
is
stretching?
because
Is it because of the stretching?
space is stretching, space is expanding. This is not we
At
were
an,
taught in schools in
it's not
when
even
we were
constant.
kids.
It's not even expanding in a constant speed. Okay, it's exponentially expanding basically.
It's
So the
accelerating.
stars that you one small fact. Okay, sorry to cut you off, Madhu.
Go
The
ahead.
stars and all the galaxies that you see in the sky right now, maybe in the next 10 billion years or so, you won't see any stars at all. I mean, like
So I won't be
our
there in the stars as well.
yeah, not there will be stars, but
No,
they
no.
will be so
That means
far
that I
away.
won't become a star after I die.
Of course, you
You
won't.
will become a star, but we won't. Your children won't be able to see you.
Yeah.
Nicely put.
So
Okay.
basically, universe is expanding so exponentially fast that, like in maybe I don't know the time frame properly, but at least in the next 10 billion or 15 billion years in the future, the people who come after us, like if humanity is present till then, they will never know space as we know it right now. So you can say that we are living in a very awesome time in the birth of the universe, basically. So we should be happier for
Yes, yes, I am happy.
that.
So yeah, touching on that point, the what is making the space time stretch as we know it is uh, something called
Dark
this
energy.
dark energy. Dark energy. It's just because we have a name for it doesn't mean we know
We
what it is.
know.
So we don't know what it is. That is why it's called dark. So this is the energy that's kind of pushing space away from each other. So the like Amir was saying, there will come a point in time, very many billions of years into the future, wherein you look up at the night sky and there'll not be a single speck of light, not a star to be seen, because the universe would have expanded so much. The space between the stars would have expanded so much and pushed everything away so much that they would simply be invisible to us, right? So yeah, that was dark energy, which
Wow.
is expanding space time.
This is insane. We started with black holes, and now we know that there won't be anything. After some time,
And we
there won't
haven't
be any
even got
stars.
black holes properly yet.
Yeah, exactly. You just ruined it for me, bro. You literally ruined it for me. You just
No,
told me
there
that
was
there won't be any stars anymore, so I will not become a star anymore. I will become a star, but no one will be able to see me.
no.
That,
You shouldn't feel so bad because right now, like see, like as you know Dr. Neil deGrasse Tyson, right?
of course.
As he says, like the universe is in us basically. Every single atom in our body is like we can like date it back to the stars that died for us basically. We are
I think
basically star stuff. I don't
Yes,
know if I'm explaining
yes,
it properly.
particles.
I think Madhu can like add on it more.
We are
But
particles of
basically,
star. That's
yeah,
what Mr.
yeah. You basically the
Explained that.
universe is in us, right? Because
Right.
every single atom or every single particle we know of, every single thing, everything came from somewhere, and maybe like some of it came from a dying star, that they are dying star like uh, tens of millions of years ago. Basically, you may be made up of one part of the star, and Mr. Madhu may be made up of like other part of the star or something like that. So that gives you a perspective. Basically, we are all connected. So
Hmm. All right. So,
So,
Madhu, I want to ask you, like,
if I
uh,
may, if I
huh?
may,
Sure.
uh, so the black hole, the basic structure of a black hole is, you can say, roughly speaking, you can divide it into three parts. One is the singularity, the stuff that you never see, the very core of the black hole, around which is this blanket of just dark stuff, the event horizon. So that's the point of no return, as Amir was saying. Once something gets into the past the event horizon, that's it. It's never getting out, because we'll come back to this. And the third part is the accretion disk. The accretion disk is the disk surrounding the black hole. A very, probably not the right example, but a very close one, nevertheless, would be like rings of Saturn, right? Or all of us, most of us would have watched the movie Interstellar, and there we have the closest simulation that we can have of a black hole. Very realistic, though they did miss out on one bit. I'll get back to it later. But if you remember that sequence, you have the massive black hole,
Mhm.
Gargantua. If I remember it
yeah,
right,
it's same
Gargantua,
Gargantua.
Gargantuna, something. Yeah. So the black hole, and then there's a ring around it, and then there's a ring over it as well. Have you noticed that? So there's a
I'll
ring.
have to see it once again. I'll have to watch it once again.
So there's a
I'll,
ring around it, and there's a ring over it,
oh, yes,
which
yes, yes.
goes
Right,
around
right,
like this. So
right.
it's not like it has uh, morphed rings or something. It's just that uh, the black hole is so dense enough that not anything at all can escape it. So it's warping the space around it, right? So the space is getting warped around the black hole, around the black hole. So the light that is going around the black hole, because space itself is warped, you're able to see the back of the black hole. And what does light do? It just travels through the medium of space-time. Now when space-time is warped like this for you, the photon goes around the black hole and comes up like this and goes on again. So it's not really, this is not the real path of it. The real path of it is still the normal ring around the structure, but because the space-time is warped, you see this, and the back side of it coming up like this, and then around it. So yeah, so these are the three basic uh, uh, shells of a black hole, if you may call it. So
Mhm.
one more point I would like to add here is, whenever you look up what a black hole is, the very first thing after saying what it is that the gravitational field is so strong that even light cannot escape. It is not entirely true, because light is not trying to escape it, even with all that speed, the momentum it has. It's just following the path of space-time, right? So space-time is flat. There is no black hole, just the sun and the Earth. The okay, the sun here and the Earth here. Now there's just space, and light always travels in a straight line along the medium of space-time. Okay. Now you just drop a black hole very close to it. So what happens is, space-time is no more just flat. It's warped completely 360 degrees. So when space-time is warped, What will light do? It won't travel this way. It just travels through the curvature of space-time. So because all the space-time is getting inside the event horizon, or it's all just uh, everything is spiraling inside into the center of the black hole. Light is just going through the straight line that it thinks it is, but for us, we know it's no more straight. It has been curved, so light cannot get out because the space is curved. Not
It's
sure if
just
this
taking
was
the path of the
clear
space,
enough.
basically.
Yeah, but light follows a straight line along the path of space. Now, when you bend the space, light just goes this way. So that's what's
Oh,
happening inside the black hole. That is why light cannot get out of it, because there are no roads leading out of the black hole. All the roads are leading inside the black hole, and light simply follows it.
And one more fact about light is photon. There's no concept of time for photon. I mean, time never passes for a photon. I
oh,
think that's a different huge topic that we can talk about maybe in a different podcast. But since we are like more into black holes now, maybe we can talk about like why our sun can never be a black hole. Like before
before
that,
that, before that, I have one question before that. I know that that is one of the list of questions which I have prepared. One of the questions is why our sun cannot become a would say
black hole.
black hole once it's about to die. Because I read it somewhere, or no, Mr. Tyson, he actually told in one of his what do you say
Lectures.
podcasts or some lectures or something that it will never become a sun can never become a black hole. So yeah, that's one of the topics which I want to discuss with you guys. But before that, I want to know, like, as you said, like, we have a picture of black hole. How was that taken? Like, what, like, how was that image actually successfully taken?
That
Is it
was his
accurate?
biggest scientific feat, actually. Like, I think Madhu and me, we were like both on our like, we were both smiling, and that day was the best day of my life when they pictured a black hole.
I
We were
had goosebumps. I had
literally,
my eyes were welling up when I looked at that picture of the black hole. Oh my God. Can you beat that? We were able to
Right.
photograph, I mean, in theory, we were able to photograph a black hole, something that had never been seen. And
I
until
think that
that
is
evidence, people even thought that there were uh, uh, other thought processes going on, that such a thing may not really exist, but all the mathematical equations were pointing to such a dense body. And finally, a picture. Oh my God.
that is the day that the whole Earth became a telescope. I mean, that
Yeah.
is the time the whole Earth became a telescope. And to put it in a different way, that is the time when the whole Earth became united, basically. That
Right.
to
For
take
our
that
viewers to
picture,
understand, so for our viewers to understand the image what we are talking about, I have put out an image here. I hope people are able to watch it. I mean, you can actually relate what they are actually trying to tell you. This is the image which exactly what Madhu and Amir are explaining to us. So this is exactly the image. All right. Please tell me, how was this picture taken? Please tell me. How can Earth become a telescope? How can that doesn't even
Go on, Amir.
fit? That doesn't
no,
even
I don't have the specifics for that, but I think 14 or 15 different telescopes from around the world, 14 or 15, I don't take me up on the numbers, okay? But all the telescopes around the world, they took the like synchronized themselves in a such a way that they focused on a point in space. I mean, the black hole the that was captured was M38, right?
M87.
M87, sorry, M87. This was the M87 was a supermassive black hole. We'll come to supermassive black holes later, but that was the photo that was captured, basically. So now, do you know how like photograph? Like, do you know anything about photography, Mr. Richard?
yes, kind of.
Yes, a bit.
Exposure and all those things, right?
Yeah. A photo
So,
point.
like there are
Yeah.
some pictures you have seen of what do you say, Milky Way and all such things.
Right, right, right.
These are long exposure pictures. Okay,
Exactly,
so
exactly.
the aperture is kept open in the camera. Examples, my small example. Aperture is kept open on a camera for maybe like 1 or 2 minutes so that all the light comes in into the aperture.
It can
So,
capture all things. Yeah.
yeah, all the light, as much light as possible. That is when even in the dark, if we have a good camera and the aperture is exposure is kept open for a long time, so at that time what happens is like you will be able to like see even in the dark on that picture. Okay, same thing applies to the black hole also.
Mhm.
Basically, black hole is black. We can't see any, like, we can't, if a black hole doesn't have a accretion disk or a event horizon, we would never be able to see the black hole basically. So since it has the accretion disk is made up of like all the, like the mixture of all the particles, photons, and different particles
Basically,
basically.
all matter that it can find,
Yeah.
or that a black hole can find in its vicinity,
So this
probably
is
came
what
from
happened. Like
stars or nebulas.
all the telescopes around the world synchronized in such a way that they took their sensors to one specific place in the space time. They, I think they, for it to be captured, it took around 1 or 2 years, right, Madhu? Like, uh, timeline, I'm not sure.
Yeah. Uh, hmm.
It was like series of images. It was not just one single image. Okay, it was not even images. This was data captured by those
Oh,
sensors, and all the data was taken, and terabytes of data, not even terabytes, like
Penta,
petabytes,
petabyte, petabyte.
petabytes of data was taken, and then all this data was what do you say, combined in one platform. I think a machine learning model was used by a very beautiful lady. I don't know her name.
Oh yeah,
I think
I forgot her name. Yeah.
I think she was the biggest, like, if you have to give credit to someone for this photograph, I think she deserves the biggest credit, because she created a machine learning model that combined all this data and created an image, and that image was like, since you saw the picture here, that if you see that image, it seems like it's just a donut or something, donut captured in
right,
low light
right.
basically. But the time it took for that picture to be captured, and the, like, effort it took for that picture to be captured, and the unity around the scientific community it took for the to take that picture. What if someone knows, like someone reads history about that thing, no, like they can actually uh, know what it is basically.
So yeah, that beautiful lady was Cathy Bowman.
Yeah,
So
Cathy
let's
Woman.
just put her picture here.
Yeah.
Oh,
So
yeah.
Yeah.
thanks to that lady, we have a black picture of a black hole that was theorized by Einstein long back.
Uh,
We are still solving Einstein's problems. Imagine, he was the teacher to all of us. He left us with homework, and we are still solving his homework problems, basically.
Very
actually,
nicely put. Yeah. So uh, yeah, basically they did use telescopes, radio telescopes all around the world,
Radio telescopes.
because uh, like it's easy to ask, why do not we have a picture of the American flag on the moon, which was set there by the Apollo astronauts who went there? Because every time they
right,
went, they put a flag down there. Why can't we see
exactly.
it? It's possible, but it's just that there is not enough motivation to go ahead and put your resources, build a telescope just for that, to capture that. It's very much possible. But it would be extremely difficult as well because the size of the telescope would have to be huge. The dish would have to be extremely huge. Now imagine what you are looking at is 55 million light years away. An object that is 55 million light years. Just to get a sense of it, the time taken for the light from sun to reach us is 8 minutes, and
Right.
for that same light to reach from the sun to Pluto, the last X planet, was around 4.5 hours. And
Whoa.
the last time we sent a thing for it to capture Pluto, it took it 10 years to reach from the Earth to Pluto.
Yeah.
And it's 4.5 hours away for the sun, for light. And imagine this, 55 million light years away. It takes light 55 million years to travel that distance, and you are supposed to capture a photo of that object.
So the
Yeah,
black hole
easy
will
peasy.
be so the black hole which we actually have the picture is 55 million light years away.
Yeah.
It is. It is a supermassive black hole right at the center of the M87 galaxy, Messier 87. It's named after this guy, Messier, some guy. He was basically hunting for comets.
Okay.
He wanted to have a map of all the comets, and he was making a catalog of all the stuff that he saw. And this
Uh-huh.
thing did not look like a comet, so it was uninteresting, but he still cataloged it. So Messier 87 was the name given to that galaxy. And after the discovery of this, I mean, after the picture of this black hole, they had to come up with a name for it, right? Because M87 supermassive black hole does not have a ring to it. So they came up with this Hawaiian name called Powehi, I guess. Yeah, that's how you say it. Powehi. 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 Yeah. It means some uh, exotic thing in Hawaiian. But yeah. Uh, so yeah, the amount of engineering and the brain power that went
Yeah.
into getting this
So,
is
but
immense.
how
So this
how did they capture that image which is 55 million years away from us?
exactly, over a long period of time, you build a telescope the size of the planet. So realistically, not possible at this stage in our civilization, at least. So you build multiple telescopes or use existing telescopes that are all across the planet. So around three or four of them were in the U.S., in the states of Arizona, Hawaii, and one more, I guess, and then in Mexico, and then in the Atacama Desert, and then in Chile across South America, and then one on the European continent. I guess that was in Spain, and then one on the South Pole, Antarctica.
Mhm.
So this is what they could get their hands on at that point in time. But now there are a lot more telescopes around the world that are coming into this project so that they can map other black holes that are out there. Probably we may even get a sharper image because yeah,
Mhm.
in this day and age when a selfie camera can capture even sharper images, you show someone who does not have an idea of what a black hole is, the image is not too impressive for a person of like that. But with with many more telescopes joining for this project, it's called the EHT telescope, the Edwin Hubble telescope.
Uh-huh, uh-huh.
Got you there. It's the Event Horizon telescope, not the Edwin Hubble
Oh,
telescope.
oh, oh.
So
I heard Hubble telescope. I know Hubble telescope. That's the only telescope I know. I don't know about other telescopes.
So yeah, EHT, the Event Horizon Telescope, is a project, a consortium of all these multiple radio telescopes. Like you can see in multiple wavelengths of light, radio waves, X-rays, gamma rays,
Hmm,
right?
hmm.
So infrared and visible light. Hubble sees in the visible light spectrum.
Okay, okay.
So for if you want to see an object that is extremely that is at cosmic distances, a telescope looking from a light spectrum is not enough because it is emitting. information or radiation in various wavelengths like X-rays, gamma rays, infrared, visible, and stuff. So they had to build telescopes which can pick up radio wave signals, that wavelength.
Mhm.
So in effect, they made a huge, and practically speaking, a telescope spread across North America, South America, Europe, Antarctica. So just Asia and Africa were left out, and Australia. But yeah, so they built a telescope that big a size and captured that image over a lot of time, and it took them 2 years for them to get that image. They captured all the data that they could,
But to
and then
assemble together, yeah.
yeah, to assemble them together, because they could not transmit the data via the internet, even via the super fast internets that are available today, because 5 petabytes of data,
True. That's too much.
you have gigabit, we have 1 TB hard disks now and multiples of TVs, and this is in petabytes. So if they worked this out, if they had to transmit all the data over the fastest internet available today with I mean standalone optic fiber lines, using it at its full potential, it would still take 25 years for them to just get all the data from all the various telescopes to 1.25 years. So they thought it's better to get it via the collect all the information, put them in the hard disk. I mean, it's all collected in the hard disk, and ship them via the aircrafts. So that's
Uh,
even, of course, faster than the quickest internet. So yeah, nothing beats the bandwidth of a 747. Yeah.
wow, that was something that was really crazy. All right, so let's go to the first question. What I had: why can't our sun be a black hole?
Good question. So uh,
Where to start?
here's the thing.
So
Okay.
I think first it's better to answer this question like how how are black holes formed actually,
Yeah, that would
right?
be better.
That question would be better put before than coming to like explaining how why our sun can't be a black hole. Madhu, we can take the stage basically.
Yeah,
Thank you. Thank you. So it's still, we don't have enough evidence, concrete evidence, which says this is what causes black holes. We have hypotheses in place as to the origin of the black holes. So and of course we have not observed anything directly, because the scales at which we are talking, human life is not enough to observe that. For So basically the idea is, if a star is dense enough to begin with, if it has a lot of matter, I don't have the numbers at hand, but if you have enough matter, what happens is, like you could say, a better way to start it would be the life cycle of stars, right? So a star is born from a nebula. All the stars are born in a nebula. The
maybe
nebula is
nursery of
area.
all the stars.
Sorry.
A nursery of all the stars. Can say that.
Yeah, beautifully put. Yeah, a nursery of all the stars. So it's just gas spread over uh, thousands and millions of light years across, and
Hmm.
all that gases over time start attracting each other, coalesce into bigger lumps, and finally they become this huge heavenly body and start emitting light, because of all the basic gases that were present, that were available when it was being born. So it starts out with hydrogen. So at the core of say the sun, all the hydrogen is the resource. It is the currency that the star has. So all this hydrogen is being used to form the next, or let me put it this way: all the hydrogen is under that immense pressure and temperature. Two hydrogen atoms are fusing together to form a single helium atom.
Right.
Okay. And now, when this happens, there's an immense amount of energy given out, and that is what is happening in the sun. So every second, every moment in time, hydrogen atoms are getting together, forming helium atoms, and in this process, emitting light, and that is the light we see. Now, over a long period of time, it runs out of all the hydrogen it has, right? Because it there has to come a time when it has used up all its resources, and what it just has this helium, which was a product of the hydrogen fusion before. Now it starts eating up all this helium, and what happens is helium fuses together into lithium. Yeah, the element lithium. Now, as lithium forms, again, a lot of energy is given out, and the star keeps continuing to do this way until lithium it runs out of helium and everything is just lithium. It uses up all the lithium to form the next element. And if you notice, this is the sequence of the elements on our periodic table.
Yeah.
The first element is hydrogen, the basic element,
Hydrogen,
which
helium, lithium.
hydrogen forms to form helium, helium fuses to form lithium, and so on and so forth, until the time where iron has been formed in its core. So there's just molten iron. Now, for molten iron to form the next element, I don't remember what the next element is, but the process tries to continue. If the star is massive enough to begin with, if that core is massive enough, it will start converting. It just stops at an iron core. Now, if the star is big enough, it has the iron core, and it has all the other outer shell, which is made out of the previous material. This iron core cannot withstand the pressure of all the outer layers of the star, and then it starts to collapse on it itself. And when this happens again, immense amount of energy is given out, and all the outer layers are blown apart, most of it on the surface, and it starts falling in on itself. It starts sucking in on itself, and this is when it becomes even dense, even huge, because there is not enough space. Everything that has existed, all the matter, it's just getting into a smaller point in space. So, like I said before, how huge an atom is if you had to just blow it out to light scales. It's basically empty space. So, because of this pressure that is present at the core of the stars, the electrons at the far reaches of the nucleus keep getting pushed down towards the nucleus. I mean,
Okay.
just imagine the amount of energy that there must be for something like this to happen. Imagine someone at the edge of our solar system pushing the Pluto body all across towards the center of the system, which is into the sun. Takes an immense amount of energy, right? At that very minute scales, it does take a lot of energy. So all the electrons come closer to the nucleus, and thereby the space, they make way for some more space, and they keep shrinking until such a point where the electrons are very close and touch the nucleus. And what happens when it touches the nucleus? Electron is negatively charged, and the protons are positively charged. So they just cancel out each other. So there is no more electron, there is no more proton. There's just the
Nucleus.
neutrons that remain.
Neutrons.
Neutrons that remain. So this happens for all the atoms in that star. It loses all the protons and the electrons, and it just has neutrons. So that is what, and that is when it becomes a neutron star. So imagine all a sun has been shrunk to the size of uh, say a 50-kilometer diameter.
Ball.
Yeah, a
50
Okay.
ball
kilometers per.
with just 50 kilometers from one end to the other, and then it would have become a neutron star.
So,
So
to
all that
understand the
big,
scale of this, it's like compressing Earth into basically a tennis ball
Okay.
yeah,
with the same density. I mean, not the density. I mean, yeah, right. Same
the same
density,
mass. Yeah,
the same mass. The
Oh,
that tennis ball will weight weigh as much as Earth basically. So you're just compressing everything. That is what Madhu is telling.
yeah.
wow.
So that is when it becomes a neutron star, which are extremely dense. So they are the second most dense things out there in the universe. The first is the black hole. The next is the neutron star. Now, if a neutron star was even bigger enough, the it still keeps the core still keeps collapsing on itself. It's so dense, right? It is so extremely dense that it's just not sitting there on the surface. It's all trying to fall to the center of the core. And when this keeps happening over and over, it becomes what is called a singularity. A point so small in space time. Imagine the sun into 50-kilometer radius, circumference, sorry, diameter. Sun shrunk down to the size of 50 kilometers in diameter. And
Right.
then that further being compressed to atomic levels, to the size
Smaller
of
than
an atom.
atoms,
Imagine
basically.
this, the entire sun being shrunk to the size of an atom.
Wow.
In fact, it's lesser than the size of that. I mean, there is no.
Yeah,
It's literally a point in space.
it's just
It's
one tiny speck point in space where Einstein's theory of general relativity just breaks down. This is what it says. This is what it gives rise to. But how do we explain that singularity? How can there be all that matter in just that one tiny bit in space, right?
How's
It's
that possible?
unimaginable. So yeah, we just still don't have an answer for that.
no
So the
answer.
best that we did last year was getting a photo of what was at the on the outside. So in the future, hopefully someday we'll be able to peer into the black hole and right to its depths and see its soul of the singularity and see
And
what it is.
coming to your question, Mr. Ruchak,
And coming back to tell that as well.
why our sun can never be a black hole is because our sun is very small compared to the suns that can form a black hole basically, that can collapse into a black hole. Our sun maximum it will become a red dwarf basically.
A
Red
red
dwarf,
giant.
right?
A red
Red
giant.
giant, sorry, red giant. And then it will explode into a supernova basically. That is all it can be. It will not be a neutron star. It can never be a neutron star or a black hole because the sun is not massive enough. Massive enough okay, that it can become a neutron star or a black hole basically. So that's the answer basically.
So wait. So you're saying that sun is not big.
Yeah,
Yeah,
our big brother is not big enough. Yes.
exactly.
So we need. So okay. Give me a rough calculation. Let's say, for example, a tennis ball is our sun, or
Mhm.
let's say, okay, let's make it a little bigger. Come on. Let's say a football. A football is our sun.
Okay.
In comparatively, how big should be the ball? How big the ball should be for it to become black hole?
I think maybe
Uh,
10 or 20-kilometer radius.
yeah.
Diameter, sorry. For it to be a black hole, our sun to be a black hole, our sun right now being a football, for it
Mhm.
to be a black hole, it has to be at least 10 kilometers in diameter.
You're
So
not
I'm
losing out any mass. All the protons, neutrons, and the electrons of the sun, take them as they are and just try to, if possible,
Compress
if
it.
if possible, this weekend, Ruchik, just try to do this. Just try to compress all of this into a 10-kilometer radius, 10 to 20 kilometer
Even
diameter. Sorry.
Definitely,
so,
Yeah,
definitely,
and then you have a black hole.
just
definitely.
fun with yourself. Compress yourself to a singularity, bro.
Oh
Basically,
yeah, like
then you
I
can
can.
become a black hole.
Yeah. Wow, that was crazy. So that's the reason why, you know, a black. I mean, sun can never become a black hole. Wonderful.
Yeah,
But it doesn't mean our sun is small. It's actually huge.
Hmm. Hmm.
it's a regular star.
Yeah,
In no way extraordinary. It's neither extremely small or extremely big. It's your regular
it's
Joe.
normal.
Yeah.
Okay.
So
Okay. In
there
that,
are various phenomena that happen around a black hole that are extremely hard to understand and even to put across. But again, as Einstein said, if you're not able to explain it to a 10-year-old, your understanding is not good enough, right? So there is still this uh,
What if we fall? What if we are falling in a black hole? What will happen then?
well,
yeah.
I know
No one
we are
knows
not
yet.
coming back.
No, but no one knows yet, right? I mean, no one knows like what exactly is on the other side.
No, but it's kind of explainable actually. See, this is all measured, but even though it is a very tiny fraction, the gravitational force that you get on your feet is more than you get on your head, basically.
Yeah.
Understood? So
Right.
because you are further away, your head is further away from the earth, gravitational pull of the earth. So the gravity has lesser effect on your head than on your feet. This is very minute. So nothing happens to us basically. So same thing when you are near the, like when you are passing event horizon of the black hole, what will happen is even the like gravitational force between the start and the end of the atom, even that will change. So eventually you'll be spaghettified. That's the word basically. You will be like spaghetti basically. You will be,
Italian spaghetti.
yeah.
Yes, the same one.
You'll be spaghettified. That's the term for it. This is called spaghettification basically.
I still okay. I didn't understand. Come on, start again. What is spaghettification?
Spaghettification. When
So
you're, yeah, Madhu, please.
so imagine you are drifting close to a black hole, right? You are upright. You have the head at the top and the and your feet pointing down. So you are drifting closer to the black hole. And what happens is, like Amir said before, it's not like your entire body is pulled in at one in one go. The closest thing that is to the point of no return, the event horizon, is what leaves you first. And it's not like your legs will get torn apart. It's even um, intricate
Crazier
than that. It's
thing.
even intricate than that. You will be literally able to see your atoms get pulled right from you, right underneath you. You can still see this, and if you don't have a heart attack, you'll still live to see until your legs are pulled inside in streams of atoms, like you have spaghetti. So
You
that's
will
the origin.
basically get stretched basically.
Yeah.
You watch this movie. Do you know this superhero, Marvel superheroes called Fantastic Four?
Yeah,
Yes.
yeah.
There is a guy in that, like, oh shit,
Mr. Fantastic.
Mr. Fantastic.
The elastic
He
guy.
stretches, yeah, elastic
Yeah,
guy.
yeah, yeah.
That's what will happen to you basically when you're near a black hole. And then imagine like you're falling into the black hole, and I am like maybe 2,000, 3,000 miles away from you. Okay,
In a safe
now
distance. Yeah.
in a safe distance,
At a
I'm
safe
just
distance.
watching you. You will
Bye, Ruchik.
you will become spaghettified. Okay, but what I'll see is I just see you right there. I mean, you will be stuck in the event horizon, and then slowly, 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 your light fades away. I will not see that you have been spaghettified basically. I just see you like become a small blip of light and then you vanish basically.
So is it a theory or is it a fact?
It's it's a
No,
it's a theory
in
basically.
science, one point on that. In science, when you say a theory, it's tested. It has been postulated. First, it has been hypothesized. The idea comes up, and then you come up with all the equations that can support what you are saying, and then you pass it across to other peers, and they test it, and you make observations, and the observations fit with what you are saying, and then it becomes a theory. So when you say a theory, it's not like in our day-to-day language where theory is just our idea or concept. But in science, a theory is as good as fact, as close as it can get to a
It's a
fact.
proven fact basically, scientifically proven fact.
So it's a proven fact that spaghettification really happens.
Mathematically at least.
Yeah,
Okay.
yeah, yeah. Because yeah, nothing leaves you, right? You get stretched completely, and all your atoms get streamed down to into the event horizon. And what happens to Amir as we okay, I'll be by Amir's side looking at you getting spaghettified. So what we will see is just you hovering on the event horizon and just getting dimmer, 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 and until there is nothing to be seen. It's not like you'll just disappear all of a sudden, or that will watch you being stretched and all. This is because time, it's again the medium of the universe is space time, right? That's the fabric of the universe. Now,
Right.
time slows down inside a black hole. Times,
Right.
or to put it, time slows down at the event horizon and stops at the singularity.
Singularity.
There is no time, there is no space. There's just one point. Okay. So the light rays from you, Ruchik, to us are not coming either. So what we are seeing is the last time you were very close to the event horizon.
Mm.
So you are still just you are just about, let's say you are a step away from that point of no return. So that's the last part of you that we'll see, because that is the last light that has left you and reached us.
Okay.
After you take that step, you're no more there. So there is no light to bounce off you. So for us, you'll just be there, and as the light deteriorates, there is less and less of light coming to reaching us. It will just you will just appear to us as if you were there and just vanished into thin air.
Wow.
This is all mind numbing, mind boggling, and yet captivating.
And
My
still
God.
there are like so many facts you can tell about black holes. Like we spoke about the birth of the black hole, the life of the black hole, what will happen to our life if we go near a black hole. I think it's like we can end it by saying how a black hole can die. Black
Yeah,
holes can die basically.
Black holes can die.
Yeah,
So what
of
will
course,
they
dude.
become?
You don't know anything that has birth has to die.
yeah.
But this is something. It was a birth of a
And
star, which
it
actually
was
made it a
rather
black
proved
hole in the end. It
rather
became a
theorized
black hole in the
recently
end, right?
also. It was rather theorized recently also. You know, by
What?
our favorite Stephen Hawking.
Uh huh.
He was the one who theorized that the black hole can die, but the death will be so slow. black holes will be
Excruciatingly slow.
black holes will be the only objects in space that will be alive even after everything has died. Everything in the universe has died. Black
So
holes
basically,
will
it
be
won't
the
die. It
they
will
will
see
die.
everyone die and then he'll die.
Yeah, basically. So this is called Hawking. They die. Uh, the term for that is Hawking radiation. Huh? because Stephen Hawking was the one who theorized it, and so sad that he passed away so soon.
Yeah.
He had so much, and he was the like. I wish he was there when the black hole picture was shown.
Yeah.
That
Yeah.
was his life's work.
Yeah.
He spent his life writing about black holes, researching papers about black holes, and even award-winning fact like Hawking radiation. He proved Hawking radiation. So it was very. He died like months back before this picture was released, right?
I guess so. Yeah, I guess so. I
That
mean,
was the baddest, saddest part.
a brief history of time and black holes and baby universes was my the only book that the very first book that I read, which was not from school or from the library. It was not a storybook. It was not a novel. It was it was nothing else. This was the first book that I read, and it was of Stephen Hawking. Yeah,
I still have his book, Theory of Everything.
yeah. I have that book, though it's not mine. I just took it
Yeah,
from a friend
you
for
should
return.
watch that movie, Theory of Everything. You will understand him like crazy. His sacrifices, the sacrifices he made, crazy those are. Even after his what was the name of his condition, Mr. Muthu? I don't remember.
Electroneuron disease. It's a kind of an electroneuron disease, but I don't know the exact name either.
It's okay, Ruchik, don't cry.
Uh, yeah.
We are sad too.
We are
All
So
right.
sad too.
Let's.
here's one another thing. I mean, there's just so much to speak about black holes, man. We have
I think we
barely
can
scratched.
create a second part about black holes again.
Exactly.
Actually,
That's what I was about to say. Like, what
That.
if
Yeah.
we can just, wrap it for today? And before wrapping, I just have one last question for you guys. Uh, which, where is the nearest? I mean, in our Milky Way, how many, like, in our Milky Way, are there any black holes?
there are many black holes. Like our
So why
Milky
did
Way
you paint a
galaxy
picture of?
has a
Uh-huh.
super massive black hole in the center of our Milky Way galaxy. Basically, every galaxy will have a super massive black hole in the middle. Basically, that is the
So,
holding force of our whole galaxy. I guess
so it is important to have a black hole, basically,
it
what you're saying.
seems so. It seems so.
It seems
Like
so so far. Yes.
every galaxy scientists have observed till now, they find a supermassive black hole in the middle. Basically,
Okay.
that
And
seems to be the holding force.
so, okay, in our Milky Way, if we had it in our Milky Way, if we have a black hole, why did they go for the picture of this black hole rather than going to some other black hole in some other galaxy?
Good question. Uh, so the thing is, and a very valid question too, because it is in our own backyard, and the distance from us to this. Okay, by the way, before addressing it as it, let's address it by its name, Sagittarius A star, right?
Sagittarius A star.
That's the name of our supermassive black hole. So
Sagittarius A star. Oh,
yeah.
okay.
Oh, A star. That's where they came up with the name for the car, A star. Okay.
I think.
So
Oh yeah, and now
Sagittarius A star.
Okay.
So yeah,
black holes are very shy. They won't come on pictures much. Basically, so it's
to
very hard to find a black hole. It's not
Yeah.
at all easy because they
I
don't emit light and such. Okay, and then the only reason we were able to capture the black hole at the center of another galaxy was because it had too much matter around it. And of course, if it had matter and photons, of course, it would be very bright. Correct. So
right.
that is when we would be able to picture it basically. Now, if a black hole came right beside you in the dark, you won't be able to see it basically. So, like just as an example, so black hole is black, literally black. It's like there's no light anywhere in the black hole. So imagine picturing something like that. It will be very hard. So like we will all we'll be able to detect is the effect that is left by the black hole, not the black hole, right?
Oh,
Something which is black, you can't picture it. So even though that picture that we showed like some time back, right?
mhm.
Even that picture in the middle, it was just a hole. The only reason we were able to conceive that it was a black hole because there was light around it. Correct. So
Right.
black hole is basically invisible. If there
So
was no matter around it, accretion disk around it, we wouldn't even be able to see it basically. Yeah, Madhu.
yeah, uh, so the Sagittarius A star black hole is around 25,000 light years from us. In comparison, M87 supermassive black hole is 55 million light years away. So, in practicality, it should have been easier to look at this. But uh, I forgot the numbers. The our supermassive black hole, as supermassive it is, it's tiny compared to the M87 supermassive black hole. So the amount it's occupying in space right there is small, one thing, and there is a lot of stuff between us and the black hole there. So we are not even on the same plane. Like roughly speaking, Earth and the black hole are not on the same plane. So all the there is a lot of stars and matter that are blocking our view from Earth to this black hole. First of all,
Mhm.
this is very tiny, and there is other matter obscuring its the radio waves and other forms of waves coming through. So it's hard. But at the same time, why they picked M87 was it is extremely huge, around 2000 times bigger than our Sagittarius A star. Okay, so M87 is 2000 times bigger than this black hole, and it's thankfully it's also, or we are pointing towards the black hole.
Uh-huh.
So and there is not much disturbance or other objects between the path of light between that black hole and us, our planet. So when you have a huge black hole to begin with, and then there is not much disturbance between, it will be easier to point your telescopes at it than pointing at something that's smaller and murkier. So yeah, I guess the plan was within this year or the next. They wanted to release the picture of our Sagittarius A star plus. So
Oh.
we'll get to see that.
Right. If we start talking about all these things, I mean, especially black holes or anything in space for that matter, it's a never-ending topic. I can completely understand. So, and you guys with me, I can keep on talking about it for a whole night for sure. But I think we'll have to give it a break, and we will
Yeah.
have to come back again. I have a
We'll
lot
come
of
back with black holes basically.
right. I will have a,
For-
I have I have a list of several other questions as well. So I think in the next episode we can continue with there. What thing?
yeah.
Yeah,
Right.
definitely. Would love to.
All right. So guys, thanks a lot. Thanks a lot for joining us, and
This is
thank you,
fun.
Madhu.
This was fun. Thanks a
Yeah,
lot.
thank you, Madhu. Thanks, Amir. It was really,
Pleasure.
really good. And I literally went back to a better science class which I've ever joined in my life, I guess. So I hope I had a time machine and I could have made you my teachers back then in my school or something. I would have been really good in studies by now, for sure. So,
Well, you are good at a lot of other things as well.
well, yeah. All right. All right, guys. I hope you guys enjoyed this show, and please let us know how you like it and what you would like the most. We will try to inculcate most of the things, whatever you tell us. And please don't forget to like, share, and comment below this video, and let us know what you like to know more about and what would you like to add on our podcast. All right, so It's good night and have a good day, guys. This is Ruchik Divakaran signing off from A3R3 Quandary. This is In and Beyond by A3R3 Quandary. See you next time.